Our session today will be on theory. Production theory. So what is production? So in taking about production, we are looking at the conversion of goods into conversion of raw materials into output of services. So this is a fundamental concept in micro and managerial economics where we examine how we convert these inputs like the factors of production into output, which are the goods and services. So production theory gives us insight of the relationships between the resources, the production processes, costs, and efficiency. So the key components we're going to look at in this section will be basically um, inputs. What are inputs? We'll be looking at the factors of production like labor, capital, and entrepreneurship. We also look at outputs. What are outputs? These ones will come in terms of um, the goods and services that are produced. We also look at technology, which will look at the method of combining these to produce output. We also look at the production function, which is given by Q is a function in terms of labor and capital. So this is what we are going to look at. So in our production function has those general form. Q, which is the output, F, the function in terms of capital, K, L for labor, M for materials, and other variables that we may look at like land, energy, etc. One thing we must take cognizance of is that when we are dealing with production, it can be production in the short or the long run. So in the short run, at least we must understand that one factor of production, usually capital, is usually fixed, whilst other factors like labor are variable. But in the long run, we're assuming that all inputs are variable. The firms will adjust both the labor, they also adjust the capital. So the long run, these are all adjustable. In the short run, capital is minimal, so it's fixed. You only variate the labor factors. So we have graphs in production theory which have points joining uh, um, points that are joining output, which is the same. So we have isoquant 1, isoquant 2, isoquant 3. So these, like in different scales, are lines joining points that offer the same output. So isoquants are curves or lines that represent combinations of inputs that will yield the same level of what? Output. It is similar to the indifferent scales. So what are the properties of these um, isoquants? What properties can you see as you see them? They're downward sloping, they're convex, okay? They are parallel, they don't crisscross each other. So we can have the unit of labor and capital, as you can see. So the output for isoquant 3 is higher than 2, which is higher than 1. Okay, so 3 is the highest. But when you're looking at the optimal production, it's simply at the point where the isoquant kisses the budget line. So this is what we call the marginal MRTS, marginal rate of technical substitution. It's the point at which output and the budget line meet. So we must understand those important components. So what have we said quickly? We've said that number one, these isoquants are downward sloping, they're convex to the origin, and they do not intersect, they don't crisscross. Okay, these are the properties. All right. So if that is clear, we can proceed. So we're going to look at how to optimize these indifference curves. We're going to look at how to optimize these in different scales using what we call the Lagrangian functions. Using what is called the Lagrangian functions. So there are three stages of production that we're going to look at. The first stage, second stage, and the third stage. Before I go to explaining these three stages, I'll go back again to say we have production that is in the long run. The long run production always has one item that is fixed, and that is the short run. The long run, all inputs are variable. Here, only one variable. So isopoints are lines that are joining points. The properties are that they're downward sloping, they're convex to the origin, they don't intersect. So those are the key properties if asked. Okay, then we go to understanding the stages of production. So we have these stages that must be understood by the curves. So number one, we have stage one, where we have what are called increasing returns. In this stage, okay, so these stages are very important. For stage one, the marginal product and average product are increasing, okay? So they are both increasing. Okay, the marginal product of labor. Then in stage two, the marginal product begins to decline, but remains positive. In stage three, the marginal product of labor becomes negative. So this is stage one, stage two, and stage three. The average product is increasing in stage one. In stage two, it is still rising. Okay, in stage three, it will fall. So this is average product of labor. So this is how the curves will look like. So these stages of production are very, very important. Now the law states that as more of a variable, there's what we call the law of diminishing returns. So as more of a variable of input is added to a fixed input, the output will initially increase at an increasing rate, then at a diminishing rate, and eventually will decline. So we look at this as the law of diminishing returns. So there's a key concept that we usually use in economics, which is called returns to scale under the long run analysis. Returns to scale. Remember, we talked about the long run having all inputs change proportionally. So we have what we call increasing returns to scale, constant returns to scale, and we have what we call the decreasing returns to scale. So when dealing with increasing returns to scale, output will increase at a greater proportion. So using graphs, you can illustrate those returns to scale as follows. So increasing returns to scale, your output would be doubling. For instance, this is 10, 20, 30. So, or 40. It's doubling. So this is increasing returns to scale. Decreasing returns to scale can be increasing but at a reducing phase. So this is 10, this is 20, this is 25. It's increasing but at a declining rate. Then at a constant rate, 10, 20, 30. So this is what we call a constant returns to scale. We have what we call increasing returns to scale, or what we call diminishing returns to scale, and we have what we call constant returns to scale. So these are the three levels that we need to understand. So they refer to how output changes when all inputs are changed proportionally. The increasing returns to scale is a situation where output will increase by a greater proportion than the inputs. Constant returns to scale is where output increases by the same proportion of inputs, and decreasing, the output increases by a smaller proportion than the input. So under production also we must understand that there are terminologies that we must acclimatize ourselves with in terms of the formulas. So there's what we call total product of labor, average product of labor, marginal product of labor. So all these key terms are important to understand. So what do we mean by the constant, the total product of labor? Okay, what do we mean when dealing with the um, average product of labor? So these are some of the key terms that we must understand. Okay, so we'll use some graphs, some tables to illustrate that. So we have the output, total output. When you divide it by quantity, or divide it by labor units, we call this the average product of labor. The change in total product, when you divide it by the change in the labor units, we call this marginal product of labor. Anything marginal is addition. When you apply this marginal product of labor times the price, it's called the marginal revenue product. So this is the marginal product, marginal revenue, times the price. So whenever we want to be economical, we should ensure that the marginal product of labor is greater than the wages or equal to. So this is the consideration we must always have when we are dealing with what? Production. So we must ensure that the marginal product of labor is greater than the cost. So we'll give an example in terms of tabulations before I go any further. Give an example in terms of tabulations before I go any further of those formulas and their applications. Okay, so in the event that you're given your labor units 0, 1, 2, 3, 4, and 5, and you're given the total product of labor, which follows the law of diminishing returns of 1, 3, 5, 8, 8, and 6. Okay, how do you find the average product of labor? Do you remember? We divide the total product of labor over the labor units. So 1 divided by 0 is infinite. 3 divided by 1 is 3. 5 divided by 2 is 2.5. 8 divided by 3 is 2.33. 4 divided by 8 divided by 4 is 2. 6 divided by 5 is 0.2. Then what is the marginal product of labor? The additional units. So from 1 to 3 divided by 1 minus 0. So what is our additional units we're having here? We have 2 units. From here to here, another 2 units. From 5 to 8, we have 3 units. From 8 to 8, we have 0 units. And from 8 to 6, we have negative 2. So this is following the law of diminishing returns. So in any normal setting, you must understand that total output sometimes will increase, but under saturation, it begin to decline. But the marginal product will begin getting negative at the point when it exceeds the maximum point of the total product. So this is how we show this. It's a change in total product over change in labor units. So in the event that we are told that are there any questions so far?
I think everything is okay so far.
Everything is okay. Okay, just a minute. So it's clear. Are we
Yes, it
together?
is.
All right, okay. So suppose, are you able to calculate the marginal revenue product? Suppose the price was 10 kwacha. We multiply the marginal revenue by 10. Try that.
Oh, just to confirm, is it not 10 by 3 for the first one?
Yes, we multiply the marginal product by, so marginal revenue product is simply what? The marginal product times what? Times the price itself. So suppose our price is 10 kwacha. So we're going to multiply 10 kwacha times each of these ones here. So here we're going to have 12, 20, 20, and we have what? 30, and here we have 0, and here we have negative 20. Then suppose our marginal revenue cost or wage, I told that is 30 throughout, 30 kwacha. So how many laborers must we employ? So we need to employ where the marginal revenue product is equal to their cost. So we're going to employ at this point, how many workers are we going to employ? 3 workers. So wage should be equal to marginal revenue product. So sometimes the question will come to calculate the number of what? Workers to employ. So we employ when it is equal. All right. Are we together?
Yes.
All right. So we now need to go to what is called the Cobb-Douglas function. Okay, the Cobb-Douglas function. So there's a type, common type of Cobb-Douglas function that we should acquaint ourselves with. We've talked about what production is. I think by this stage you know what production is. It is simply the what? The conversion of the raw materials into output. So, and the production function is given by function in terms of labor and capital. So the Cobb-Douglas function is a type of function which is given as follows here. So A stands for efficiency or technological factor. A and B are simply the elasticities, how responsive output is. So this is what we call the Cobb-Douglas function. So that is what we are going to use now to calculate efficiencies. So now, if you're given a question like this, for instance, since we learned how to differentiate, if we're given a question like this one here, we are told um, production function is given by 100, K 0.6, L 0.4. The marginal product of a capital MPK is simply the additional units that we are going to get from keeping a labor constant. So we differentiate. So we do partial derivatives. So dq over dk. We're differentiating with respect to capital. So we'll leave the what? The A as it is. There's nothing to do. So we're going to differentiate 100K 0.6. So you multiply 0.6 times 100, we get a 6. Then subtract 1 minus 0.6, get 0.4. That's how we differentiate. Are we following the differentiation that I'm doing there?
Yes.
Okay. So this is what we call the marginal product of what? Of capital. Then we're differentiating with respect to, so this is called the marginal product of capital. If we're differentiating with respect to labor, let's differentiate this. So this is dq over dl. It's the marginal product of labor. So what is our dummy? K 0.6, right? What are we going to remain with? 100K 0.4. So we differentiate 100K 0.4. So 0.4 times 100, what do we get? A 4. Then we subtract 0.4 minus 1, what do we get? L negative 0.6. Are you following?
Yes.
Yes. So that is a marginal product of what? Of labor. So now we've been given that suppose the capital is 25 and labor units are 100. Let us calculate the marginal product of labor and marginal product of capital. Suppose labor is 100, capital is 25. So if we're told that labor is 100, capital is 25. So what is a marginal product of labor and marginal product of capital? So this one, what is the marginal product of labor? The negative guy will go down just to rewrite it. So this will be say 4K 0.6 over what? L 0.6. Are we clear on this?
Yes.
So where there is K, we put what? 25, 0.6. Then here we have L is what? 100 and to the power 0.6. You can use a calculator to calculate that. Similarly, here marginal product of capital. If we're going to rewrite it, how do we write it? 6 what? L 0.4 divided by K 0.4. Then we substitute. Where there is a L, we're going to put what? 100 power 0.4 and capital, we're going to have 25 to the power 0.4. So what do we get in that regard? Are you calculating? Do you have a calculator there with you?
No, I don't have.
Okay, so I'll calculate it for you then. So when we calculate our MPL is giving us our MPK is giving us 104.3. MPK is giving us 104.3. And our MPL, when you calculate it, it's giving us 17.4. Okay, just punch that in the calculator as it is. So the managerial implications here that our MPK of 104.3 is much higher than the MPL of 17.4. So this means that capital is currently more productive than labor. So as a manager, you need to invest more in capital, like machines and technology, to increase what? Efficiency. But you also need to balance up. It is needed because at some point the returns to capital may diminish. So the potential challenges that you may likely face are that high labor relations. So if you over rely on machines, they may lose their jobs and workers may resist. The other issues are that you may face what? The technological risks. Suppose there are rapid changes in technology and investments may make those technological assets obsolete. Then also diminishing returns. Up beyond a certain point, adding more machines without skilled workers will reduce effectiveness. So this is how this is supposed to be looked at. So this is coming from our exam paper to understand this question now here. So given the marginal product of labor, okay, given this question here, calculate the marginal product of capital and labor, and as a manager, what do these values mean for the firm, and discuss um, if you invest more, in what potential challenges will you have? Okay, so this is clear, right?
Yeah, it's clearer. With practice, it will be more clear.
Yes, 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 yes. Okay, so that will be your homework. So we do the second question, then we end. I'll need that homework as usual, the way we do it. All right. So let's look at question number 6B. These are exam questions, so I need you to really take them seriously. So mathematically show mathematically that it exhibits the law of diminishing returns with respect to capital, then discuss any three properties of the Cobb-Douglas function. Then we end there. So the law of diminishing returns, we have respect for it. Let's see whether it is showing. So we know that if we have a negative value, the law of diminishing returns will exist. So let's do the partial derivatives. How do we differentiate that? How do we find the MPK and the MPL for that? How do we find the MPL and the MPK for that? So in this case, dq over dk. This is our MPK, and your product of capital. So what is our dummy? Our dummy is L what? L.5, right? And what are we differentiating? 25K.5. So 0.5 times 25, we get 12.5. 12.5, when you subtract 1 minus 12.5, the K becomes minus what? 0.5. Is that clear?
Yes.
Then we do the second derivative of this one to check whether there's a law of diminishing returns. So we also differentiate again the MPK, or if I differentiate it for the second time, we just put a 2 there, and here the K, and we put the 2 there. So let's differentiate this again. So our dummy is what? The L again, L.5. So we're going to differentiate 0.5 times 12.5, we get negative what? 6.25. Then the K, we subtract 1. So 0.5 minus 1 is negative 1.5. So from here, we can comment, does this exhibit the law of diminishing returns? So since there's a negative here on this A, back, negative, okay? So it shows that diminishing returns exist. So as more capital is added, there's a negative also on the exponent here, the extra output shows that the extra output from each unit of capital will decrease. So this is showing or evident that there's what? It follows the law of the diminishing returns. Okay? This exhibits or shows that the law of diminishing returns exists. So it's very important to understand from the differentiation. So using the Cobb-Douglas, the 25 is the factor that stands for technology. So the 0.5 on top there is a exponent for K and 0.5 for L, meaning both at that stage, labor and capital contribute equally. Then when we add them, because remember there's constant returns to scale, increasing returns to scale, and decreasing returns to scale. So from the powers, you're able to tell when you add them and you're getting 1, it's constant returns to scale. So here if we had K, and here there was 0.1, and here there's 0.5 as it is, it would have been diminishing returns to scale. But here if there was 0.6 and 0.5 there, when you add them, it's getting 1.1. This is increasing returns to scale. So as it is, it's constant returns to scale. Okay, so to know or ascertain whether there's a law of diminishing returns, so you need to differentiate twice. The first derivative we found 12.5k minus 0.5 was the 0.5 on L. So for that first derivative, it simply means that for any given level of labor, if we increase capital, output will raise, but it will depend on the k.05 factor, which means that uh, it will decline as k begins to become bigger. So when you do the second derivative again, we found a 6.25 negative and k minus 1.5 and L 0.5. So we also have a negative here. Since the negative, it proves that as k, which is capital, increases, any extra output from each additional unit of capital decreases. So this verifies the law of diminishing returns. So we have explained that K stands for capital, the number of ovens, in this case, L stands for labor, the number of bakers. One oven and many bakers, productivity is low. 2 to 3 ovens will increase the baking. Okay, 50 ovens, but 2 bakers, again, is not too good. So many ovens may be unused. So you need to add more laborers to operate that. So that is where the law of diminishing returns comes in. So we need to be practical as much as possible. So the key properties of the Cobb-Douglas function are that if you have a positive but diminishing returns, it means that either K or L, while keeping the other constant, will increase output, but the increase is small at each time. So for instance, you may have 1 to 2 machines that will give you a big boost of 100 to 101 machines. Okay, so the returns to scale, if you have a 1 there, that's constant returns to scale. If you have greater than 1, increasing. If you have less than 1, decreasing. So the power is also what determines what returns to scale you have. So capital and labor can potentially substitute each other. Right. So my homework for you be to do this question here. Question number 6, which we are just from doing. Please do it religiously. Is that okay?
Yes, I'll do it.
Thank you so much for your time.
Okay. Thank you.